Yeah, so as I was saying a few seconds ago, today is just mostly a review because we already finished all the material for the exam. Let me just show you a couple of things before we start, which would be useful for you to keep in mind. So let's see. Oops, yeah, here we are. Oop, okay, yeah. First of all, if you go to the department website, you can already see the solutions posted for the practice exams on MyLab. So if you need to check them out, there they are. I hope to post tomorrow, but tomorrow will be the last day. I mean, the latest that I will give you the grades from of the exam on Monday. I was just waiting. I mean, I'm still waiting to see if we can have the letter grades by tomorrow, because it's sort of more useful to release the grades together with the letter grades. But if the letter grades are not decided by tomorrow, I'll still post the grades so that you can see it before the exam, so that you have a better idea of where you stand. At least like for now, like right before the announcement about the final exam, the solutions for the previous midterm can be found already on the website. So you can click here if you want to see the solution for the midterm. But anyway, so again, like I'll probably tomorrow should be the latest that you'll get to see your exam grades. So, and then we'll have yeah, as I was saying, I'll give you some review on Wednesday, and the TA Tariq probably will give you some review either sorry, office hours, and like probably Tuesday or Thursday you should have also extra office hours for Tariq. But in the meantime, like, you know, if something comes up, you can always email me throughout the week if you get stuck on something. Okay, but any questions maybe before we start, like just doing some examples? So far so good. So let me start sharing the well, I think you also saw that, but I created an announcement with the class grade, so you can check it out if you haven't already. If you got 100 points and you're good to go, like that's the most you could get on the classwork rubric. Like the other points are about the midterms or the finals. So, but and if you like, you can email me if you had like any questions about the grade. But yeah. So let me start first with an example about Stokes theorem. So imagine, let's do this example first. So I give you a plane. This is a plane with equation 2x plus 2y plus z equals 1. Oops. Okay. And the question, imagine like, okay, so again, like a plane is like a piece of paper. So imagine that you draw on this plane your favorite curve in the world, like, you know, a closed curve. So this is a completely arbitrary closed curve that I'm drawing on the plane. And the idea for this example is that we want to use Stokes theorem to show, let's call this curve that I drew on the plane C. So I want to show that 2y dx minus 3z dy minus x dz only depends on the area of the region enclosed by the curve. So by that, I just mean that, you know, like you drew a curve on a piece of paper. So there's some area of the plane that's trapped by this curve. So let me color it. Okay. Let's try to work this out. So first of all, this is not like a notation I have used many times, or I don't know if any time throughout the course, but like what does this mean? So let's just try to start. Let's start by figuring out what does this mean. Like one way to do this, like which is convenient, is to rewrite this as a dot product. So you can just copy the coefficients. So you can write this as 2y negative 3c negative x dot dx dy dc. Is that making sense? Any questions up to this point? So far, so good. So this is actually the dx dy dz is like a notation, alternative notation for writing dr. So this is like what you would have seen as a vector dr. So this is like the dot product of some vector with dr, right? And like the integral of f dot dr, that's basically the work, right? So this is really like, so we're really, this is secretly, so what we're trying to find here is the work of, so we're finding is that making sense so far so good? Are there any questions about this?
Curve C is the purple stuff.
Curve C is right, it's just like that purple stuff, correct? Yes.
And it's not defined.
It is not defined, right? Like, so that's why, right? So that's the thing. Like, if you were to try to find the work directly, right? You would need to parameterize the curve. But like, how are you going to find the parameterization if I just drew like, you know, like just some crazy picture, right? So like
Does it have to do with the plane?
it's just right, it's just like some curve that you draw on the plane, but like you don't know what it is, right? It's not, you don't know if it's like a circle that you drew on the plane or the triangle, like it's just some random picture on the plane, right? So like the point is that you cannot just try to solve this by computing the, you know, doing this integral directly, because like you don't have the parameterization of the curve. Is that making sense?
So how do we get one? How do we get a parameterization of the curve?
Good. No, that's the thing. Like that's the magic word at the beginning of the problem, that it doesn't it tells you to use Stokes theorem, right? So the
So
point
you
about
use it to find the area instead?
well, what you'll see, but like the idea, and we're about to do it, but like the idea with Stokes theorem, remember, is that instead of doing like the integral directly over the curve, you do the integral over the surface determined by over a surface determined by the curve, right? And so the surface that I want to choose here for Stokes theorem is like this sort of like region whose boundary is like this region on the plane whose frontier or whose boundary is a curve C. Is that making sense?
That makes sense. So is that why you have the plane there? Because you want to subtract this purple region from the plane?
Well, it's not so much that I want to subtract it, but the thing is like, right, good thing that I'm surrounded by cables. So, you know, imagine like this is kind of like the curves that we're talking about. Like it's like a crazy curve, right? Like something like this. So in Stokes theorem, right, when you trying to find the work along a closed curve, you have to find like a surface, right, whose boundary is this curve. So the idea
Yeah,
of
kind of like the top of a cup, just the top of the cup.
right, and so the idea of drawing the plane is sort of, it gives you like a hint of which surface you could use, because again, like there's so many possibilities, right? Like for a circle, like all of these could be things that work. So like the idea in this problem is to tell you, oh, choose as a surface the region that got trapped in the plane by the curve. So that's like the one that I'm drawing here. So that's the purpose of the plane, just to give you like a natural candidate for the surface that you should choose. So here the surface for Stokes theorem will be like the part of the plane whose frontier or whose boundary is that curve, like the piece of the region of the plane okay. And so again, like the idea is that you can turn this, thanks to Stokes, into a double integral over the surface of the dot product between the curl of f, and remember you have to put like this cross product of the parameterization here. So like here, like as in any Stokes problem, you have to find the curl, and separately you have to find the parameterization of the surface. So let's start with the curl, just because that's not too bad to do. So again, like what's the curl here? So f was 2y 3z negative x. And so the curl of f, if you remember it, is this determinant business. So you get -3, and then you get 1, and then you get what? -2. So this is the curl. So far, so good. Any questions about this? So okay, that's the curl. By the way, just a reminder, the curl always computed first in terms of x, y, and z. So this is like an important reminder. Meaning that you don't, even if you're going to do something where you're going to write X, Y, and Z in terms of like R and theta or other coordinates, other variables, you always find the curl first with Cartesian, and then you just change it into whatever variables, new variables you want to use. Okay. And so now we have to parameterize the surface. Yeah, we have to parameterize the surface. And again, the surface is just, let me draw the picture one more time. It was just this piece of the plane. Oh, like here I already even like did like a different picture for the curve. Doesn't really matter. Like the point is that the surface is a part of the plane, right? So when you are trying to parameterize it, you're really just parameterizing the plane itself, right? So really what we have to find is like a parameterization of the surface of the plane.
So would that mean that we would have to work with some kind of unknowns that we replace with letters, depending on which the purple curve would be changing?
Well, no. So like the thing is like the curve only plays a role in like the parameterization of the plane, right? It will be the same regardless of how you drew the curve, right? That's fine because it's just like what changes would be like the bounds for X and Y, right? Because you're not you're not parameterizing it, like like the parameterization has two pieces. First, like it's just like giving everything in terms of two variables, right? That can be done regardless of the curve that you drew. Where the curve plays a role is just when you're trying to say what values, like say X and Y take, for example, if that makes sense. So the parameterization itself is sort of unaffected by the curve. It's only the bounds of the parameterization that get affected by the curve. Just to give you an example, imagine that, imagine just to make it easier, that like the plane had been like something parallel to the XY plane, right? And one curve had been like a triangle, and the other curve had been like a square, right? So like in this case, the region would have been something like this, the interior of this triangle. And in this case, the region would have been like the interior of the square. You see, but both of these like are parts of the plane. So they have the same parameterization. It's just that for the bounds, they would be different, right? Because like these are sort of like the bounds related to a triangle, and these are like the bounds given by a square, right? So the bounds will change from given like a particular curve. Is that making sense?
Yeah, so that's what I'm asking, because we have no information about the curve.
Oh yeah, but like yes, correct. But the statement of the theorem, of the example, was just that you just have to show that this thing depends on the area of this region. Like, so it's not asking you to give like,
oh, okay.
Right. It's not asking you to give like, oh, it's 10, right? Or 15, right? It's just saying that whatever answer it is completely determined by the area. Yeah. So, right, because I agree, you would not be able to like give like a number per like 5 or 10 for this type of problem. But you'll see that it's enough to like, at least you have enough information to say how it depends, like how this answer depends on the area trapped by this curve. That's basically what we're trying to do. So what's the parameters? Well, not really. In this case, I thought it was 2, or maybe I changed it. Let's see. Oh, yeah. I mean, it was. Sorry. Thanks for. It won't matter because, well, yeah, it won't matter for the parameterization, but my intent was 2, right? Sorry. Thanks a lot. Yes. So in this case, we cannot really find the bounds, but the point is that. You don't need to know the bounds for what the problem is asking you to find, so it's fine. So yeah, so the parameterization of a plane, again, there are many ways to parameterize it, but like the easiest thing here you can do is like just parameterize it in terms of X and Y. So let me just use the parameterization. Is that making sense? Like, is this everyone okay with that being the parameterization for the plane? And again, once you have the parameterization, it'll move more or less automatically. You compute the partial derivatives. And then you take their cross product, right? So the cross product here well, I mean, if you do it, it just like, it's not too bad to figure it out in this case. It will give you 2, 2, 1. Okay. So according to Stokes' theorem, so thanks to Stokes' theorem, the work, remember f dot dr would be the integral of the dot product between the curl together with this parameterization. Sorry, together with the cross product of this parameterization. And so the curl, like, and like notice that I'm not writing anything here like for X and Y, because as we have been discussing, like I don't really know where X and Y go from, right? I cannot say that X goes like from 2 to 5 because I don't know like the details of the curve. So I'm just writing it like without like specifying the bounds. Like I'll say a little bit more about it in a second, but like, right, like this is kind of unspecified because we don't have that data. Right, but like my point is that that's not like a cause for panic, because of just like the problem was asking you a little bit less information for you to find out. So like the curve was -3, -3, 1, -2. And this was 2, 2, 1 dy dx. So far so good. Are there any questions up to this point?
Yeah, so just to be solid on this, the second part where we're doing the cross product of R, the vector R, that vector R is always a matter of the plane on which the curve that we're looking at lies, right? So it doesn't matter what the curve is. What matters is as long as we know the plane.
Right, because it
And only the boundaries
right.
matter. Got it. Wow. Okay. Thank you.
Yeah. Only the boundaries, like obviously the curve plays a role, but in this case, it only plays a role for what you would have liked to write for, like, the two bounds for the integrals, right? Because no, if you look at all these pictures, no matter which picture I'm drawing, I'm just coloring some part of the plane, right? All of these things, and so they are all contained in the plane, and so the parameterization is kind of the same.
This makes so much sense. Thank you.
Okay, good. So when you do the dot product, well, this is not a difficult dot product to do. This is like -6 dy dx, and we're getting close to like, you'll see now why like this question kind of makes sense. Like, remember a constant, you can just take it outside an integral. So you're just integrating, like this work is -6 times the integral of y1 dy dx, right? And so far so good. Is this okay? And so what if you have a double integral and you're integrating? Yes, good. The only thing, right. So you see, like, this is why this is related to an area, right? Like the only thing is like, what type of area? Well, this is like the area. Maybe like this is like maybe a concrete example would. Let me do it like here, so that like this makes more sense. Like again, if the plane had been something like this, right? When you figure out the bounds for X and Y, you're actually sort of looking at like at the shadow that this region makes on the XY plane, right? Because that's how the XY bounds are determined. So really like these bounds for X and Y, you have to imagine that any of these pictures, sorry, like for any of these pictures, it's just like a bit difficult. Like I'll try to draw it this way. I think this will look fine. Like the point is that even if you had like a curve here, like you should imagine that for figuring out the bounds, like this makes like this curve and region draws like a shadow curve and shadow region on the XY plane. And so like that's like strictly speaking how the bounds would have been determined. So like if you're doing like this integral is like sort of like the area of the shadow region, right? So like but my point is that the area is just like, sorry, the answer is just -6 times the area of the shadow region. Is that making sense?
Yep.
In fact, yes. So right. That's because the y-dx only calculates the area in the xy plane. Correct. Yes. Yeah. So what this is saying, so what, like, just to conclude this, like what this said is that the work is -6 times the area of the shadow. Okay. Just give me a second. Is that making sense? Is that any questions about this? So like, interesting, like this is where like equations somehow give you like an interesting perspective just by moving them around. Like what this is telling you is that the area of the shadow is -1/6 of the work, right? So you can also, so this is like a more like of a remark, right? Like in this particular case, that the area is -1/6 the work. So that means that if you somehow had like a way, right? If you somehow had like a way to find the work, right, along the curve, that sort of determines the area, which is kind of cool because like the work, you know, when you do an integral of work, you're doing like the integral along a curve, right? So this is saying that somehow the area can be determined by knowing something that's going on along the curve, along the frontier, right? So in fact, like there's a device, you can, they don't fabricate them now, but you can, I got this one from eBay. There's a device called the planimeter. Like, let me type it on the, which kind of looks like this. I mean, I would need to, it has a couple of pieces, so I'll need to put them together to show you how it really works. Actually, there's a video on the course side if you want to watch it that explains how a planimeter works. But the idea of a planimeter is literally that, like you would draw, when you have a planimeter, when you have a planimeter, like for example, if I wanted to find the area of this region trapped by the pink curve, the planimeter works as a device that you just move around the curve and it will give you the area. So the planimeter is like somehow like a device that computes the area just by moving this compass or like this pointer along the curve. So that's a very cool thing. And so you can like, again, like that's better explained in one of the YouTube videos that I posted on the Canvas site. But like that sort of tells you that, you know, somehow you can find like the area by doing like an integral over a curve. And in fact, there's like a similar principle where you could find like a volume by doing like some sort of surface integral. So like if like, you know, this is kind of useful in medicine, because like say you want to know like the size of a tumor, or like something like, you know, you cannot open up a patient and cut it just to measure like some part of volume, like how big it's some sort of like region in your body is. But like, so if you wanted to determine the volume, but you have like a way to do like the measurements along the surface could be like the exterior of your body or something like that, then you could find the volume. So that like it's like sort of like the same principle operating. But like what these theorems allow you to do is sort of like, I mean, if you think about it, like what they allow you to do is like exchange doing integrals over curves with surface integrals, or in the case of the divergence theorem, surface integrals with triple integrals. But that sort of goes both ways. So it's kind of like, that's like why the theorems are sort of useful. Is that making sense? But yeah, just find the find type, like it's one of the YouTube videos. It's just that I think I didn't ask that one for you to watch on the quizzes, but it's posted along with the other quiz videos. So if you you can find this one there.
Is this a sort of problem that we could be asked on the final exam?
Well, this is a yes, although probably for the final exam, it would give you like, in order to just get like a number, it would tell you that the area of the shadow is like 10 or 15, right? You know, like it would give you like a specific value for the area, so that you can actually give you like the actual answer. Is that making sense?
So can you explain again why the area is the reciprocal of 6, -6?
Well, I'm just saying like, sorry, I meant here area of the shadow. Oh, well, I mean, like I'm just saying, like we just found this blue line, right? Like this is what we found from our calculations, right? And so you divide by -6 of both sides of the equation, you can sort of solve for the area, right?
Okay, I see.
So I'm just saying like that, I mean, like the whole point of an equation, right, is that you can like, it's like up to you to decide which side you want to think of being determined by the other, right? So if you write it this way, you're sort of thinking of the work as being determined by the area, right? That the moment you know the area, you multiply by -6 and you get the work, right? But another way to think about it is that if you somehow had like a way to know the work, like a different way to find out the work, then the moment you have the work, you divide it by -6 and you would get the area back. Is that making sense?
Thank you. Yes.
Yeah. Yeah, so it's just like, you know, it's like the psychology, right? It's like just psychologically speaking, like a change of perspective of the equation, right? So good. Let's do now an example about the divergence theorem. Let's see. Okay, so here we'll use Here we'll have as the region, like here, the 3D region will be the stuff like inside the cylinder. Below the paraboloid. And above the XY plane. So you mean this thing? Like what I'm just writing? Well, they wouldn't use the word stuff, but they would say just like the region inside the cylinder, below the paraboloid, and above the XY plane. Like except for the word stuff, everything else would be more or less exactly the same. Yeah, like or like I mean, you know, in some situations there might be a picture, but like in words it would probably be written this way. So let's just try to figure out what like this is referring to. So inside the cylinder, let's go first there. What's the cylinder? This is a cylinder of radius 2. I mean, again, strictly speaking, it's like a circle. It's just like when you include the z variable, you get like a circle for each value of z. So that's how you end up with a cylinder. So like our region of interest is all the stuff that's kept, like you just have to look at everything inside the cylinder, right? You shouldn't consider anything outside the cylinder. But there are other conditions. So then you have the paraboloid, right? So again, this is sort of like a salad bowl. So it looks kind of like this. And let me draw it more like this. Oops, I think I know what's going on. I need to draw it more like this. No, it looks better. So this is a paraboloid, right? And so we're looking at the stuff below this paraboloid, meaning that somehow you would think of the paraboloid as the roof for the region. So but at the same time you have to be inside the cylinder, right? So what I'm talking about is something like this. And the reason why I don't keep drawing something more is because we have to be above the XY plane. So maybe I should try this again, but do this more carefully. So meaning that the XY plane is sort of like the floor, right? So this is like the floor for the region. So the XY plane is the floor. The paraboloid is the roof. And the cylinder are sort of like the lateral walls, right? Is that making sense? Can everyone see the picture? So let me draw it a little bit better, just because like now that we have like a preliminary idea of what we're looking at, because now we can focus on like what really matters. So what I'm saying is that we have something like this. So that's like the 3D region that the problem is referring to, right? Is that making sense? Let's call this 3D region R for region, right? And so like this is like I can think of it as some sort of like modern house, right? Like a funny architecture. So let's go to GeoGebra, in fact.
So the two pictures you draw are just the same thing?
Yeah, they're the same thing. It just it looks, I think, slightly better on the second one, but yeah, they're the same. So so essentially what I'm saying is that you have like a salad bowl. This was in color blue, I think, on the picture. And then you have the cylinder, right? And so you see like, and then like this gray thing is a plane, right? So essentially we're looking at the stuff above the gray plane, the XY plane, that's trapped, right? That's below the paraboloid. So below this blue bowl and like surrounded by the cylinder. So this is like the 3D region that I'm talking about. So that's kind of it. Is that making sense? And so let's draw it like this. And so you see the boundary of this 3D region, right? Remember the boundary are sort of like the frontiers or the walls. So what are the boundaries of this 3D region? Well, first is the roof, then the part of the cylinder is a part of it, and then the cylinder, and then like the disc on the XY plane at the bottom, right? So let me write that here. So notice that the boundary of this region is a surface consistent of three things.
When you say the 3D region, you're not talking about the volume, are you?
I'm talking about I mean I'm talking about that something that you need like a triple integral to. I mean, I'm not asking for the volume per se, but I am asking for like something that's like, you know, would require like a triple integral to, if you were to find like you know, something about it. I'm just saying, yeah, it's something that does require like a triple integral, right? Because it does.
Because of Green's theorem?
Well, here there's no Green's theorem because Green's theorem is really just for regions on the XY plane, right? Is that making sense? In fact, the one that I mean, this would be an example of the divergence theorem. And so remember that for the divergence theorem, it's about like a surface and the stuff enclosed by the surface, right?
Oh, okay.
Yeah.
So
Right,
flat related things.
so the surface here would be like the bottom disk plus the roof plus the lateral walls, and the stuff enclosed will be this 3D region. It's just that it's somehow easier to start with the 3D region and then just say what the surface is. So let's think of like that. I give you like a vector f, which will be 2y 9xy minus 4c. So the idea is to use the divergence theorem to find the flux of f through outward flux of f through the surface S. So like again, like what the divergence theorem says is that the flux of f, here's where like the divergence theorem is used. Remember that the flux is like an integral that takes place along the surface. So in this case, it really is like three integrals because they're like the surface actually has like three subsurfaces. So like you need to do like the flux through the bottom disk, then the flux through the sides, and then the flux through the paraboloid. So those are three integrals. Is kind of a lot. But thanks to the divergence theorem, you can do instead just like a triple integral of the divergence over the region R. So that's what we were going to try to do. So what we need, I don't know if you remember, but we need to find first the divergence. Like the divergence is a lot easier to find than the curl. So let's start there. Remember that the divergence is just the sum of the partial derivatives of the entries with respect to the corresponding variable. So first entry would yes, correct. The divergence theorem only requires like the surface to enclose something, because otherwise there's no natural candidate, you know, on what you would put for the triple, like for the triple integral, right? So for example, my butterfly net, right? You cannot really, strictly speaking, apply the divergence theorem to the butterfly net because, like, you know, the net itself does not trap or enclose anything in space, right? So what bounds would you use? What you can do if you want to apply the divergence theorem is that secretly you can sort of like add like this disk that you see here, right, at the end of the net, and then the net plus the disk is something that to which you can apply the divergence theorem. Is that making sense? But yeah, like the surface always needs to trap and close something. So you may right. So you have just to be careful, like be aware of that. So this gives you 0 plus 9x minus 4. So the divergence is just 9x minus 4 in this case. Is so far so good? Any other questions? So what we have to do is integrate 9x minus 4 dv, where the region of integration, again, like was the stuff here. So what would you say? How would you do this integral? What would you use to integrate it? Good, good. Cylindrical is like the easiest thing to try. Excellent. So let's try to find the bounds here. In cylindrical, this becomes z equals r squared, and the other one becomes r equals 2. Excellent. So it becomes like integral, integral, integral. What does 9x minus 4 become? It becomes 9 r cosine of theta minus 4. Remember that dv in cylindrical is r dz dr d theta, right? And then we just get to the point of finding the bound. So what would the bound for the theta be? Zero to 2 pi, right? Because it's sort of like symmetric with respect to the z-axis. What are the bounds for r?
Zero to 4.
Well,
Sorry, 0 to 2.
0 to 2, yes, because the radius is 2, but yeah, correct. It's 0 to 2. And what are the bounds for z? Good, 0 to r squared. And in fact, again, if you find it useful, you can always draw the picture for cylindrical. It's useful to draw the picture on the CR plane when there's like symmetry. So on the ZR plane, this looks like this. Sorry. And so that's like the shade, like the cross section that you see. And that, like, once you start rotating that cross section by 2 pi, you recover the 3D volume. So that's more or less like, and like now, I mean, doing this integral, it's like not too bad. So once you do it, you get negative 32 pi. Is that okay? Any questions about this?
Does this relate to the first problem that we did?
Well, the first problem is really was about Stokes, right? And like they're sort of separate from one another because divergence is like surfaces with 3D regions, and Stokes is curve with surfaces. So what they have in common is that there's like a surface involved, right? But I mean, they do not, you should think of them as sort of like separate theorems. Yeah.
Okay.
There's actually, I mean, there's like a way, like a grown-up version to rewrite Stokes and the divergence in such a way that they just are like special cases of like a bigger theorem, which sometimes is called the generalized Stokes theorem. And that's sort of like the one that works like in any number of dimensions, for vector, like, in dimension 4, dimension 5, dimension 6, whatever, like there's like a version of a generalization of all these formulas. And so then if you work out the generalized formula, like you get like a special cases like the divergence theorem or Stokes theorem. But for us, you should think of them as completely separate from one another. Although strictly speaking, they can sort of become special cases of something even bigger. Okay.
Thank you.
Yeah, sure. Let's do another one about the divergence theorem. So now, again, let's see. I will use as my region. So the region will be inside the, it will be on the first octant. When you say first octant, that just means, you know, that that everything will be with X, Y, and Z positive, right? So that's just what that means. So that just means X, Y, and Z are positive. And then it would also be inside the elliptical cylinder. So what's going on here? Well, so like if there were no four, in this case, that would be sort of like a circle, right? If there's like a four, that just means that you have an ellipsoid. So an ellipsoid, I mean, in terms of drawing purposes, it's just like a, you know, a circle that you have flattened out or like, yeah, made fatter in one direction, other the other. So like, not that this matters too much, but like the ellipsoid could, I mean, it could look like this. And I'm not drawing like the full ellipsoid because, like, again, we're just looking at the stuff in the inside the first octant. So all that, this is all that we need to know. And again, it's called a cylinder because like there's like a copy of the ellipsoid or the circle for each value of Z. So you end up with something like this. So I'm just drawing like the portion of the cylinder that is sort of our that interests us for this problem. Can everyone see it? And then now we are going to look at the stuff. So again, the cylinder itself is sort of infinite. So those are, again, like some sort of lateral walls. And thus we need a roof, and the roof will be the stuff below the plane y plus z equals 4. So what's the plane y plus z equals 4? Well, so what you can draw, y plus z equals 4 is like the equation of a line on the yz plane. So it's something like this. And then you just copy that line, and so you get, that's how you get this plane. So that's the plane here. And so you see the I'll show you the GeoGebra picture in a second. But oops, let's see. Yeah, I mean, this is fine, but I should do it a little bit better, because like if you look at this picture, this is a point on the cylinder. This is a point 0,4, and this is a point 2,0,0. And for the line is 0,40 and 0. Okay, now this looks better. So what will end up happening is that the cylinder and the line the cylinder will cut the plane somewhere. So that's what we're looking at. And so the roof is sort of the part of the plane that got trapped by this cylinder. Is that making sense? Let me show you on GeoGebra what's going on. Okay. So that's the plane, right? So this is how the plane looks like. The color that I used here was this one. So that's like how the plane looks like here. And then we had 4x squared plus y. Oh, let me write it this way. Y equals square root of 16 minus 4x squared. Okay, that's like, I'll do it. Okay, I have to do it in a slightly different surface. How much height do I need? Let's say 4. Oh, cute. Everyone sees the. Can everyone see the? This is the part of the ellipsoid. Does that make? Does the picture make sense? So we're looking at that sort of like, I mean, like this is sort of like from the inside of the room, right? If this is the room, the floor that you see is the the floor that you see is the XY plane, right? And then the roof that you see is like this part of the plane, and then the lateral walls are the ellipsoid. So I should, strictly speaking, put like y equals 0 and x equals 0. So that's like really like how the like there are some extra walls, but like those are more confusing. Okay. So and again, let's think of, that's a 3D region. So this is a 3D region, and then the surface will be, the surface S will be the boundary of this region. Okay. And so if I give you a vector F, the idea, again, similar to the previous problem, would be to use the divergence theorem to find the flux of F through S. So it is not too difficult to check the divergence. So what's the divergence in this case? It would be like the partial with respect to x gives you 4z. The partial with respect to y gives you minus 3x. And the partial with respect to z gives you 4z. So you get negative 3x. So that's the divergence in this case. So by the divergence theorem, the flux equals the integral of the divergence of f. So it is the integral minus 3. Okay. So now comes again the nice question, which is how do you set up the bounds for this triple integral? What will you do? What can you do?
dz dy dx. Or,
I think you said something, but I cannot hear you. What did you say?
uh,
Can you type it? I cannot hear you.
dz dy dx.
Correct. Yes. Like in this case, like cylindrical is not optimal just because, like, you know, the equation of an ellipse in polar is not that good. So you don't gain much by trying cylindrical in this problem. So what we're going to do is do dz dy dx. Excellent. Yes. So let's start with the z bounds. So what are the bounds for z? Remember that you have to do vertical arrows. I'm drawing them here on the picture. Excellent. Yeah, you have to, like, they all start at the floor, which is the XY plane, and they all exit through the roof with this, which is the plane, and the plane needs to be written in terms of solve for z. So those are the bounds for y, for z, and then where do the arrow, like, how do you find the xy bounds? Well, you have to look at where the arrows are coming from or emanating, and they are all emanating from this region, right? Which is the stuff contained by the ellipse, right? So what you have to find are like the bounds for the shadow, but the shadow is determined by the ellipse. So let's try to draw it here so that it's a little bit more clear. So right, like you see the shadow region in this case, it's just like the stuff inside this ellipse. And so if you want to use the order dy dx, it's like using vertical arrows here. And so what are the bounds? Right, excellent. You have to solve for y. So you put y equals root of 16 minus 4x squared. Excellent. And so you put here this. And finally, what are the bounds for x? Bounds for x are 0 to 2. Is that making sense? Any questions about the x bounds? And if you do this triple integral, you should get negative 40. Is that okay? Any questions about this? Good. Let's see. So yes, I think that like we only have 10 more minutes, but more or less like these were like all the problems I wanted to do for today. Oh, why is it not for oh, right, because you have to solve for y, right? Oh, sorry. Yeah, I see what you're saying. Like there's a should be a 4 here. Thank you. This was a typo. That's what you were saying. Excellent. Thanks. Yeah. Good. So yes, I think,
Professor,
yep. Yes.
one quick question.
Yeah.
So why is it for the boundaries of x, why is it from 0 to 2 again?
Oh, because you have to set, like you have to find where the ellipse intersects the axis, right? And so you have to set one of the variables 0 at a time. So for example, when you set y equals 0, right? You get 4x squared equals 16. And that will give you 2, right? Let me type it on the chat. So when y equals 0, you get 4x squared equals 16, right? So you get x squared equals 4, and then x equals 2, right? So like because it's an ellipse, so it's a little bit more tricky than like with the circle, where the circle is easy to find like the intersections with the axis. But for the ellipse, you just set one of the variables at a time. So yeah, good. So so are the units of the integrand flux over volume? Well, so it depends on what units you gave to f. Like the if you think about it, so like if you like here's like say, so if f has some units, like call them u for units, and so the divergence of f has units of u over length, because the divergence like involves taking partial derivatives. When you take a partial derivative, you put like you divide by the length because it's a ratio. And so the integral of the divergence of f dv has units of u over length times volume. So this has units of area times area. So like the units of the like of this is like, so the units in the end of the flux or of this or this triple integral equals like the units of f times the area, the times units of area. Is that making sense? So yeah. So right, it depends on what units you gave f. That's how you would, but like that's more or less how you find it in general. So yeah. Good. So as I said, I'll probably give you extra office hours on Monday. Sorry, on Wednesday. I'll send the link about it. You'll have office hours also on Thursday and Tuesday, I think, with Tariq. Congratulations on surviving. Well, you're close to the finish line, but you survived another semester of COVID. But at least next semester, it seems like most classes will be in person, which is better, right? So, but you're close to the finish line. So, yeah, if something comes up before today and of the final, just send me an email. Well, so you'll have to be patient if you want like an honest answer. Like for the final, you mean like the grades for the final? It will take a couple of days. At least they should wait yeah, I mean, there are like a couple of problems. So I'll keep you posted, but oh, no, the today's exam, like the one from last, I'll post those grades tomorrow, the latest of December 6th. It's just that I was waiting to see if we would have the letter grades, but if we don't have the letter grades by tomorrow, I will still post the grades so that you see them. It's just that I prefer to give you the letter grades. I mean, to post the grades with the letter grades. But yeah, the latest that you'll see your grades for the previous exam would be tomorrow. Okay. Good. Yes. I cannot hear you.
Am I mistaken, or do I remember them already being posted at one point?
The solutions are posted for the exam. But I don't think I have posted the grades for this for the midterm of last week. Yes.
Okay.
Yeah.
I remember the grades coming out in the curve as well. But,
No, no. But I mean, by tomorrow, like you'll see them on Canvas. But right. But at least, yeah, I don't think the grades are posted yet. But good. Yeah. But yeah, again, I'll see you around. But like, I mean, if your classwork is perfect, you don't have to worry about finishing anything else like that is classwork related, just in case like there's this question about on the chat. So good, my pleasure. But I'll see you.
thank you for this.
I cannot hear you.
Thank you for the semester.
Oh, good. Yeah, perfect. Yeah, no worries. Let's see. Oh, good. Thank you for surviving all to the end, right? I'll be answering emails until probably a bit early, right before the final, which is at 8 p.m. Obviously, probably you should try to not email me at 7:55 because that decreases the chance. I mean, I reply quickly, but depending on the nature of your question, I may not have 5 minutes to write the answer. But if it's yeah, even on Thursday, I'll be checking my email for replies, if that makes sense.
Thank you, Professor. Unfortunately, I can't recommend you for next semester to anyone because you're not teaching. It looks like.
Oh yeah. I'm not. But well, no, but I mean, well, if something comes up, you can email me.
Okay. Have a good one.
Okay. Bye. See you.